I'm so happy to go after your talk because I kind of also want to talk about outliers, although in a slightly different context. But I've been thinking a lot about them because, okay, a lot of you have already heard me 1,000,000 times talk about domain adaptation. And yes, this talk is a little bit about that. I mean, it's a lot about domain adaptation, but it's a little bit about outliers too. Okay, I mean, the reason why I presumably think about domain adaptation is that, as we said, we do not have a lot of labeled data sets. So the only labels that we often kind of trust are from simulations. But then we know that all of our simulations are not really the same as the real deal. So for AI, we want to train models on something, on some data sets that we kind of understand and trust. But we also want to use them on real data. Otherwise, what's the point? Why are we doing that? So, with new observations like LSST and DESI and all of these huge data sets, we're just not going to have time to go through all of the data, and we want to have something that works, that's going to help us, of course, do all kinds of inferences with the actual data sets later on, but hopefully also something that can help us with any kind of real-time tracking or finding interesting things that last very long time that we want to follow up very quickly. In astronomy, we kind of save everything. So for us, it's not that much of a problem of like, what do I save from this whole big data set? But in experimental physics, they also have to think about real-time saving or not saving data from experiments. So this is kind of also where this whole domain adaptation topic comes into play. So this is kind of the 4 things that I want to talk about. What are domain shift problems? Just to, in case you haven't heard me speak about it again, kind of to explain what the problem is. How in AI we want to solve it so that we have models that are universal and robust and work in different data sets. And then I want to talk a little bit more closely about outliers and about more flexible methods that I've been thinking about lately, and just kind of to get us going for discussion later on, some challenges and things to think about later on. So let's start with the problem. Okay, so the problem I already kind of introduced, which is the problem of the data sets that we initially train our models on and the data set that we want to apply our AI model on, they can be slightly different. And with non-AI models, this is not always a problem, but with AI, where AI really likes to find even the small features, maybe non-robust features that the data set has and use those, that's when the problems appear. So the data set shift in astronomy often comes if you want to combine simulated and real data. Maybe your simulations have some of the physics wrong, or even if it's correct, we have to make all kinds of approximations and assumptions so that we can run our simulations in a realistic time frame. So we don't want to wait for hundreds of years for a very detailed simulation because we can't use it. Then on top of that, on the real data side, you might have detector problems, whether that's some pixel that might be wrong, or you have some correlated noise in your data because of using an actual CCD detector that maybe it's not included in your simulated data, and so on and so forth. So you have all of these real observational effects that even if you try to add them to make realistic mocks on top of your simulation, you already initially know that you're not going to do it perfectly. And then we have a separate kind of situation where maybe I don't even want to use simulations. Maybe I want to use my old amazing data set that I understand. Maybe I want to do a Sloan trained model on Sloan, and I want to use this on LSST or something new where everything is kind of different, from all of the detector details, the depth of the survey, so all of the selection functions are different, and also all of the observational noise and all kinds of these other things. So in this case, this becomes an even larger gap, I would say, than when I try to make mocks that mock specifically target a specific telescope and then get the images. So what do I do? What is how do I solve this problem? So to make this like cartoonish way for the simplest possible methods that we often start with, which are for classification or regression on some labeled data sets, so supervised learning. What we would usually do if we don't care about this data set shift problem, we would usually take some, for example, simulated images of galaxies. These are some merging galaxies from Illustris. And because it's from Illustris, I know the labels, I trust that these really are mergers. And I train my model to distinguish between these weird-looking mergers and regular galaxies. My model finds the useful features. So in this case, actually interesting pixels are the peripheries of the galaxy, which makes sense. You can find like all kinds of like asymmetric, interesting information here that exists in merging galaxies, but does not exist in regular ones. And then I do my classification. So when I show a similar type of data set to this model, of course, the model works. But if I just add observational noise and I, for example, pretend that this is now an SDSS image, even though this is the exact same galaxy behind, of course, a lot of things has now changed in the image and the model does not work at all. So this is the problem. Of course, here it's an obvious gap, but sometimes gaps are not like this visually obvious. So why does this actually happen? So I've been thinking a lot about the latent space of the model, so I really appreciated all of the t-SNE plots and all of those snake-looking things. I've seen a lot of those. So when I build a model, the model in its internal latent space, whatever the dimensionality of that is, it decides like, okay, these similar objects are in this one region of my latent space, this other class is in this other space, region of my latent space, and there is some kind of decision boundary internally so that it can judge where every new image that it sees should belong. So when I get a new data set, even if I'm for sure, absolutely sure that like it has the same classes inside, because the properties of the images are different, they're not correctly translated into the space. So I end up with a new decision boundary that does not match the old one. So of course, the results get messed up. So what we actually want to do with these domain adaptation techniques is align these properly. So you have one common decision boundary that is applicable to any data set that you can load to your model. So this is kind of the background for all of this, but it's not this is not a simple problem at all. I'm going to just have one slide of like what people usually do and why this is a problem. Okay, the domain adaptation techniques, the area of this research is very big because it is very applicable to all kinds of industry problems and applications, from self-driving cars to picking and whatever best shirt to buy from like different websites. So you can roughly divide these methods into two different types. One are distance-based methods, where in your latent space you find a distance metric, like Dewey decided to do, and people do all kinds of different distance metrics, where you want to decide and calculate how different is my data distribution 1, that I like simulations, for example, from the data distribution 2, observations, and try to minimize this difference in some way. So make it one of the tasks of the training procedure. Make it as minimal as possible so that the model actually translates both data sets at the same spot in some sense. And hopefully that also means that you can find a common decision boundary. The other options are adversarial methods, where you still want to bring the two data sets together, but it's a less explicit kind of task. Instead, for example, you have your convolutional neural network. If you're doing stuff with images, you have this part that is just a normal part where you extract features. You have one branch that is doing your usual task, maybe classifying galaxies, but you add this extra branch that tries to classify domains. So this branch only wants to know if my image is from simulation or from real data. And here you reverse the gradient, so you actually try to make this branch as bad as possible. So what this means is you extract features that are useful for classification into galaxy classes, but useless for classification into domains. So these are, you're forcing it to find domain invariant features. Use something that is going to be useless for finding the correct domain. And for that, you don't need really labels, because you just know this is for my dataset 1, this is from my dataset 2. So the training procedure goes whatever you actually want to do, classify galaxies or regress some property, plus domain adaptation loss to make the training more robust. And as I said, and this is the most important part of the whole thing, is it works when one of the domain is unlabeled. Because if you had labels on your new data, just train on the new data. So I mean, you don't have this problem then. You have it maybe if your new data is small, but then you can do transfer learning. So in many cases, you don't have good labeled data set, and that's why this exists. Okay, so what actually happens when I do domain adaptation? So now I train with simulated images with labels, and I add observed images without labels. And the model, because it has these two losses, modifies the useful features from the ones that it had initially to domain invariant ones. In this case, it decides, okay, I'm not going to look at the periphery. I don't see anything in these. I'm going to focus now on the center. And the centers of the galaxy are going to tell me enough information about if this is a merger or not. And in the end, when you train that way, you can do correct classification in both domains. I'm probably going too slow, but I want to show you some Latin spaces and some TC plots too. So this is an actual example of, I have merging and non-merging galaxies from Illustris and from SDSS. Thank you, Galaxy Zoo, for all of the labels that you have created. No, but really, like, without Mike's work. Anyway, so here I have two classes, so blue and red, merging and non-merging. These, like, see-through are simulated, and these, like, bright ones are from the real observations. I mean, obviously, they look different. Like, all of the high-fidelity merging galaxies from observations look obvious, very obvious. So this is before any training is done. You can see that everything is mixed up and the two domains are very separated. If I just train in a regular way, and I just use my simulations, the model says peripheries are important for merging class, centers are important for non-merging class. So these are highlighted. If I look at the t-SNE after training, I have over 80% accuracy, and blue and red in the simulations have now, like, kind of are starting to distinguish between the two classes. But the real data is messed up. It, like, looks at a different thing completely. And you can obviously see that in the Latin space. So this is now my real data, which is, again, still completely confused. The accuracy is 50%. It's randomly guessing. It's detached. So obviously the model does not work. So if I instead add domain adaptation, source remains the same. Peripheries for merger, centers for non-merger. But now target behaves the same. And what happens to the Latin space? Ta-da! It is now overlapping. Oh, you almost don't see that it is like but this overlapping, red and blue are like distinguished, and accuracies are high in both domains. So if my goal here is to find merging galaxies in observations, for example, and then maybe do a follow-up with spectra to get more info about them, this is a way to go. But the problem here is that this is not flexible enough. We don't have very often very clean data sets. We might not know what we actually have in our new data. Maybe now for the first time we're observing a lot of some faint objects that were just not in the old data at all. So what happens if I really want to go from old data to new data, not from simulations? So now I have, first of all, a bigger jump, as I mentioned, like you have pixel scale that is different, you have noise, PSF, limits, magnitude limits, all kinds of different cuts. And also, like, I just do not know my new data set because it's new. And I don't want to wait for years for people to study it. I really want to search through it and find interesting things. So what do I do then? I have to think about the generality, the generality of the problem. So my old and my new data can overlap in many different ways. Let's still think about classes and classification because it's easier. I might have all of the classes that overlap. I have all of the same data in two data sets. I can have extra classes on one side on the old data. I can have extra classes in new data, which is even worse because this is an unlabeled data set and I have no idea if I have anything extra here. Or you can have extra stuff in both domains. When you want to align things in the latent space, you have to align only the things that overlap. If I try to align everything, I'm gonna fail because like you just have too much of a difference between the distributions, and obviously some things should not be aligned, they're different. So we have been developing this more flexible method that actually works on the basis of contrastive learning and self-supervised learning, where I allow the AI to decide what looks similar on its own. I'm not trying to impose any kind of metric or exact thing to minimize. I literally try to just allow it to do, like, look at the latent space on its own and see if things look similar or not. So I have these three losses that do different things. The first one, and all of them, yes, all of them work basically by looking at my output vector. So let's imagine that I have 10 classes. So the labeled source domain that I call is these field circles and the solid line circle. So my first regular loss is the loss that's going to just classify the things that I know in my source domain. It uses the regular cross-entropy loss. So this is just whatever, the usual stuff. The cool stuff comes here. So I call this adaptive clustering, but it's a clustering based on contrastive learning. I make a bunch of augmentations of my data, and I say, okay, now you know, like if I augment one galaxy image and I crop it and rotate it, it's still the same image. These images have similarity label of 1. Things that were not augmented, that are actually different galaxies, they have similarity of 0. So based on this invented labels of similarity labels, just cluster things that look similar. And on top of everything, I save this in a bank so that the model actually looks at all of the labeled data and all of the unlabeled data and compares every single combination and just clusters things that look similar, both from labeled and unlabeled domain. But, so this gives me a very flexible movement of everything in the latent space. I have this extra problem. Oh yeah, I didn't move this. So these are the similarity labels. This is the regular cross-entropy loss in some sense, but just with similarity labels instead of galaxy labels. The final cool thing is that's where outliers come in, is what if I have an extra class in the unlabeled domain that I don't know about? How do I push this thing away to not mess up my domain adaptation? So I do that by adding an entropy loss. I look at the entropy of the outputs. If this is a normal looking galaxy, usually the classifier is gonna give me fairly similar output. So the entropy of this output is small. But if I have a weird one, the entropy of this vector is gonna be huge. So let's look at the entropy and move things with large entropy even further away. So based on entropy, I do this extra pushing away of the known class. Okay. So this is literally the last thing that I wanted to show you is actual results that are really cool from this. We tried to do domain adaptation between observational data sets. Very like standard problems that we might have. 2 data sets from the same telescope, different data releases. So noise levels are different. Different surveys, maybe SDSS to decals, or wide to deep field. So those 3 things. And yes, it works in all cases. We wanted to do complicated things, so yes, I had a 10 class again, Galaxy Zoo, thank you, a 10 class data set. And I said, okay, let's say that strong gravitational lenses are my anomaly class, the weird one. So I'm not going to use any labels of the strong gravitational lenses. This is an unknown class, and let's see if we find them. So these are examples, just like as DSS, 9 classes are known, decals, 9 classes, and lensing. So no domain adaptation, I'm stopping. No domain adaptation with domain adaptation. These are known classes. Yellow, that you can't very see well, is the unknown class. It is with domain adaptation pushed to the side. And yeah, it knows all of the classes, but this is actually the final most important thing. So the known accuracy is fine, but the model knows so well when things are an unknown class. So the accuracy here is 90%. And yes, we find a bunch of lenses without ever having a single lens label in the data. And I'm going to stop here, but future challenges we can discuss later. Thank you.
Thank you so much, Aleksandra. Yeah, there's a question now in the back.
Hi, Natalie Descent here. Thanks for this amazing presentation. And I would like to know, you told us that you do data augmentation, and in the case of images, it's okay, like flipping an image and so on. But what about different kind of data? Can you always do this? Worrying about symmetries, about other things like physical stuff? Can you?
Well, yeah, that's a great question. So I think you would have to invent your augmentation in that case. What is going to be the augmentation if you're doing tabular data and you're not working with images and CNNs? Then yeah, it's a bit harder, but you could probably think about it. So like if maybe yes, I want to still keep okay, like be okay with physics, but you know that some properties maybe can change. Then maybe you can try something like that. So yes, that is tricky, but again, there are many methods that do domain adaptation that do not rely on this self-supervised learning and augmentation, so you can always try those also. So yeah.
Thanks.
This is Amy Schechter. I was wondering, what if there's more than one class of objects in like the unknown? Does it just push everything it doesn't know to the side, or can it also tell you there's 2 types of unknown things?
Yes, it can. So you can, there are, well, in this specific code, the way we made it, you can make assumptions and tell it how many classes you have. But if you don't do that, it can still, based on some hyperparameters in the laws, cluster things tightly or less tightly. So you could probably get more like clumps for unknown stuff. So yeah, I mean, I haven't tested many things yet, but it definitely can. We did run some tests with different types of numbers of classes in both domains, and it still works.
Thank you. This is Louise Edwards. I'm trying to formulate my question at the same time as ask it. But so in the example of having, say, the same survey with wide fields and deep fields in the same survey, does it matter which one you know better? Like, does it matter if you're trying to go from wide to deep or from deep to wide?
Not really, honestly, because like there are too many things that are different. Things that, especially when working with images, that is more important is just to have enough data. So in this case, we went from wide to be labeled data set to deep, but you can go the other way around. So one thing that we have tested, not for that one, but like the simpler problem with like different years of observations, where we just like, in that case, we're simulating LSST, so I can like play around with the data. So you have more or less noise. And it still works. Doesn't matter if I go from less noisy to more noisy or from more noisy to less noisy. So yeah, it absolutely works. So it's more relevant about like how much data you have, how many classes maybe you have, and if you have enough of representation. So one thing that we did test is to have one extra small class just to see if it's gonna mess things up, and it does not. So if you build your models flexibly enough, it does. Yeah, you can still work, even if one class is like 300 objects, everything else is like 3,000. So yeah.
Just okay. Just a technical detail. So when you say you use the contrastive learning to do the domain adaptation, it seems like there are no positive pairs between two domains. So how does it work? Because if you want to do the domain adaptation for two domains, you probably need some positive pair between the two domains.
So it decides on positive pairs on its own. I did not have time to say this. So yes, if you have within the same domain where you have classes, you can spend computational time and just say these are similar. But for those that you don't have, you have to calculate it on its own. What we do is we rank order, so blah, 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 let me find just, okay. So for every pair, I look at the output and I say, okay, if they're similar, even if it's not looking at labels, it doesn't know. If they're similar in any way, the output options here, the numbers in the 10 values, should be fairly similar to some extent. So
you can be more specific here, because here you're still doing the same, the domain, the similarity, right?
It's all domains. So we have a bank. You have a bank. You translate everything into a bank, and you just look at all of the combinations. And then if you have, for example, the highest 5 outputs here are the same 5, we consider that a similarity label of 1. So you can play around with this a little bit.
So you do have some labels between the two domains.
So you only have labels. So you only have labels for the source domain, so in this case these, but the labels for that are actually only used for actual classification of this domain, exact domain, and nothing else. So in the similarity labels, we have this, I am using them for the label just to make things faster, but overall you don't need them. You just rank order the outputs and say, if my first 5, 10, 3, whatever number of outputs are the same 5 for the 2 examples, I will consider them close, make them close to each other. And of course this evolves over time, but you're just using this and you're rank ordering. And that's how I make all of these similarity labels S, basically. But they will change from epoch to epoch because of that movement.
You have one more question?
Yeah, thank you. Very nice. I was thinking just an extreme case for galaxy morphology, for example, in which, especially when you go from one survey to the other, in fact, the morphology can change. So the label actually, so if you observe a galaxy in a much deeper survey, you might say, oh, now I see a disk. This is not an elliptical anymore, it's a spiral. But with your alignment, you will try to push and say, no, this should be an elliptical. Because I was, trying to think loud, how will that work? If you have, some differences in the data that make the labels different as well.
So the first thing is that your new data is not labeled. Right. So I'm not going to try to push it to a spiral now because I don't have that label. So hopefully what this will do, so if your new galaxy now you resolve it better, you see that it's spiral and it looks like a spiral, hopefully the model also sees that it looks like a spiral. So it will try hopefully to move it towards spiral galaxies and not toward ellipticals. Because you're trying not to enforce any of your knowledge on the movement of things because you don't know, especially for the new data. And one thing that we have seen here is that if you have enough data that is okay, it will learn what the properties of objects are. So in Galaxy Zoo, of course, you have a bunch of things that are wrong. Even if you make cuts use only the highest possible, high accuracy labels. It has found a lot of examples where when we look at it, I do not agree with the true label. I absolutely agree with the label here. And a lot of lenses that do not look like lenses at all, so because I was mostly looking at them. So it has learned enough to make, in many cases, correct assumption what it should be, even if that's not correct by the true label. So, yeah.
Yeah, then as a follow-up, then if that works, it would be really cool to see what's the fraction of objects. I mean, if you take same galaxies, different surveys, what's the fraction of objects that change dramatically the morphology? How many just by changing wavelength or changing depth? Because then. Yeah,
that would be absolutely cool to do. And then maybe like if it's actually correct, like how we assume, then we can say +1 for AI. Trust it now. I'm always in the AI group.
All right, thanks again, Aleksandra. And thanks to all the participants. Hopefully we can continue the lively discussions at